We will now make a very hard cut on topics. While before we focus on cryptography, how to secure communication, how to authenticate against other services, and how to do networking securely, we now will turn to systems. So how to make an IT system secure and how to look at software and so on in the upcoming lectures. So this more or less represents the half of the entire lecture season. So what is system security about as the first topic in this whole series? System security governs the process interactions within a system. So if you imagine a normal IT system, like let's say an operating system, there is many different processes running at the same time on the system, and each of these processes wants to have its own security guarantees and also wants to be shielded from other processes running, for example, from other users. And there's more to it. There's not just processes, but there's also something we're going to call the kernel, which is the operating system part of the software running on your system. And how can we define this kernel and how can we trust this operating system kernel? Then we already talked about processes, how they can interact, but also we need to govern somehow which objects a process can access. So which files, which sockets, which other processes can a process access. And all this has to be governed somehow by the operating system. And how do we grant new access privileges? For example, if you create a new file, how do we allow a certain user or a certain process to access that file and with which privileges? And later on, how do we revoke these privileges again? And finally, we have to somehow, sometimes at least, confine a certain process. That is, we want to run the process, but we would like to mitigate, to limit the harm that one particular process can do to the rest of the system. So in case this process later on will be attacker controlled because there was a software vulnerability that attackers have compromised, maybe it's a better idea than to somehow isolate and confine the process. A first very important concept in the context of system security is the separation of kernel and user land. Whereas in the kernel we have the trusted operating system running, the user land may potentially execute untrusted processes. And we will now see how we can enforce the strict separation between the kernel and user. CPU vendors designed so-called privilege rings, and these rings, they are used to separate high privilege processes from low privilege processes. So we have a couple of rings. In this illustration there's two, it's ring 3 and ring 0. The basic idea is to place all user land processes into ring 3, which is the least privileged ring, and to place the kernel into ring 0. This was actually not the main intention back then when inventing the rings, but it really right now serves as the good separation between user mode and kernel land. Now back then when people invented the rings, they thought of even have more rings between ring 0 and ring 3, namely ring 1 and ring 2, and they originally planned to have device drivers running in ring 1 and ring 2, which have a little less privileges than the kernel running in ring 0, but do have more privileges than the user land in ring 3. Today, unfortunately, I have to say, unfortunately, all device drivers in normal operating systems do run in ring 0, so they do have kind of the same privileges than the operating system kernel. There's more rings that are added later on. If you talk about virtualization, then we have negative rings, ring -1, ring -2, and so on. But if you have a non-virtualized system, we have these 3 rings in common. And these protection rings, now actually these privilege rings, they help us to define what privileges at very coarse-grained manner a process should have. Is it a kernel land process or a user land process? Now, I already mentioned that these 2 rings, 1 and 2, are actually not used in practice, which is unfortunate, but the main reason why this happened is essentially that there are CPU vendors back then that, unlike Intel and a few others, they only foresaw 2 rings, namely ring 0 and ring 3, and they omitted, for simplicity, ring 1, ring 2. And they, in practice, have now forced the operating system vendors to just live with these two rings, ring 0 and ring 3. Now, what is the restriction of ring 3 processes? Now, there are several instructions that are actually forbidden to be used by ring 3 processes, so that's really enforced by the CPU. The CPU will check if the process currently issuing a given instruction is running in ring 0 or ring 3, and if it runs in ring 3 and it's a privileged instruction, it will forbid the instruction to execute. Then also, if you are in ring 3, you have no way of accessing other processes' address space, which is perfect. Like every process now in userland has its own virtual memory, and it's forbidden in principle to access the memory of any other processes. You don't have any direct I/O possibilities, so to interact with the hardware, to interact with files, you have to go through the operating system. More on that later, but there's no way you can do this directly from userland because you lack the given privileges. You can also, fortunately, as a userland process, not access the ring 0, neither code nor data, so you cannot actually manipulate any code or data lying in the kernel end. And you also have no direct access to physical memory, so it's only the virtual memory that you have to go through to eventually also access your physical memory as the process, but there is no way to directly actually access the physical memory on its own. In addition to the strong separation by protection rings, we also have a separation based on virtual memory. It's again very brutal, and the basic idea is that you take the full virtual memory of a process and split it in two halves. I'm going to do this on paper. So the basic idea is that we take a process's memory and divide that in two halves. And talking about 64-bit memory, we can actually be sure that we have plenty of memory, actually way too much memory that we could ever use. So the vendors decided to actually drop a large fraction of it, namely just to sacrifice the first 16 bits of the 64-bit address to become unimportant. And essentially then you only have a 48-bit virtual memory that you emulate. So we're going to do this also. We're going to take this portion of the virtual memory out and not going to use it. And we're going to refer to this 48-bit addressing as canonical addressing. Now, next we have two halves that we would like to fill. And we do this by simply adding 1 for one half to the user land and the other half to the kernel land. Okay? And essentially what we're going to do now is we have our address space, which starts at address 0, 0, 0, 0, 0, and so on. That's the maximum address. And here we have the address 0x, ff, ff, and so on, ff. That's the maximum address possible. And due to canonical addressing, as mentioned, we're going to sacrifice the first 16 bits. So here we're going to have 0x0000 and then ff, ff as the maximum address in userland. And here we're going to have the address 0x, ff, ff, sacrificed, and then we start with 800000. Okay, that's now our address space that we have. One half for the user, the other half of the kernel, speaking of the 48-bit address space, and the rest, the other part in the middle, we're going to sacrifice because we don't need that right now. Okay, so now we have a very good separation between user land and kernel land. That's the basic idea. Getting back to the slides. This essentially is what I wrote down here, also on paper. We now have a very good separation by just having a look at the address. And essentially, we can actually see from the first 16 bits whether we are in kernel land or user land. If the first 16 bits are essentially 0, we are user land. If the first 16 bits are set to 1, we do live in kernel land. It's a very easy separation. And within these words, we're just going to use the 48 bits. That's called canonical addressing. Now this strict separation is perfect because now a userland process can no longer access any kernel memory, right? So user mode process, even if malicious, cannot modify the kernel. This is great from a security perspective, but from a usability perspective, it kind of lacks one important feature, right? As userland processes cannot directly access their hardware, they have to go through the operating system, through the kernel, to do the hardware access on their own. So how does that work? I mean, a userland process cannot just enter the kernel and run kernel code because it's forbidden. And for that reason, we're going to introduce a new interface we're going to call the system call. And the system call actually a very important interface that lets a userland process enter the kernel land. So the basic idea is that a userland process, whenever it needs a privileged operation, has to ask the operating system for help. And the single and one interface doing so is a system call. So essentially, we as userland process first have to issue a system call, and you can imagine the system call as being one specific instruction on the assembly level that you have to call, and you're going to give also kind of a notion of what type of system call you want to do. For example, let's say you want to open a file, then you issue the file open system call, and this will in turn trigger the system call handler in the kernel. Now, technically what happens is that you have a so-called trap to the operating system, and doing so, the CPU has to elevate your privileges to kernel land. So at that point in time, you do gain the privileges of the kernel as usable process, but at the same time, you completely are restricted to whatever code is lying in the so-called system call handler. This is given the code, and it's no way you can modify the code. Now, you do whatever it takes to open the file, this example, and at some point you would have to return to the userland, and for this there's again a very specific instruction, the system call return instruction, sysret, that does everything you need to downgrade the privileges back to the userland. Now, this is a very easy process, and it's actually implemented for any type of interaction you can imagine between the userland and the kernel. And I gave one example, namely opening a file, but as you can imagine, there's plenty of more operations that userland processes need assistance by the kernel. So to do this, we normally have so-called system call tables. The basic idea here is that you have a system call number, which first of all indicates which system call you want to do. We had the example of open, and open happens to be system call number 2 in the x64-bit Linux system call table. The system call table for Windows might be completely different, and the system call table for a 32-bit system might be completely different. But if you have a fixed operating system and a fixed architecture like 64-bit, then essentially you would have only one unified system call table. And the one I'm showing here is for a 64-bit Linux as an example. If you would like to read from that file, you have to issue a system call number 0. If you would like to write to the file, a system call number 1, and so on. And the entry point is kind of the function, the system call handler, sys_read, sys_write, sys_open, and so on. And they're defined in the kernel. And if you're actually interested in the implementation, you can very much look into that. So if you're, for example, interested in sysread, it's documented in file system /readwrite.c. And there we're going to find C code that, or mixed with assembly code, that is responsible for doing the system call handler function of the sysread entry point. Now, the good question is, how do you actually specify the system call number? How does the kernel know which system call handler you are aiming to invoke? The answer is easy. You have to specify this as programmer in the so-called system call number register, which is, in the case of Linux, it's RAX. So you specify in RAX the syscall number as plain number, and then based on that number, the kernel would know how to continue. This mechanism works pretty well. The downside, however, is that this kind of takes some time. Going through the system call handler needs that you actually downgrade the privileges and upgrade the privileges and so on. And this is kind of costly, especially if you have code running in the kernel that requires a context switch, namely a switch from a userland process to a kernel process. Then it becomes actually quite heavy operation. And there are a few system calls that don't strictly need the code to be run in kernel, and that are actually called kind of frequently. Imagine, for example, that you're interested in getting the current time. Of course, reading the time is not a super sensitive operation that normally userland processes should be able to do even without the assistance of the kernel. Now, how do we do that? There is a couple of proposals. One is the so-called virtual system call. The idea is that a virtual system call runs entirely in user space, so you don't actually swap from userland to kernel land. And you do this technically by marking a given kernel page, for example, the one that contains the time, as readable or even executable. Now, the downside of this is that if you do this, you have to do this at a fixed address, because the userland process has to know which page you marked as readable, and you can actually do this only if you do this at a very specific fixed address. And this allows for so-called code reuse attacks, as we're going to see later in the lecture, where people thought it's actually possibly a very bad idea to do this, in order to gain some efficiency here, to sacrifice such a large part of the security. So people had to come up with some alternative which does not rely on a fixed address of representing the data for the userland. And one such idea is so-called VDSO, and VDSO overcomes this problem. It's a virtual dynamic shared object, that's the abbreviation of VDSO, and the basic idea is that instead of actually accessing a fixed kernel address, you first load a shared library as userland, the VDSO library, which can be located at any given address. So the code will be completely at a random address, which makes it much easier to also randomize all the addresses and prevent code reuse attacks. And VDSO runs at any address and then has some kernel page mapped again as read-only, but again means here the important difference between the prior approach and this approach is that the VDSO page, the VVAR page, how we're going to call it, the VVAR page is read-only and it's only data, so there's no code hidden, so you cannot actually do code reuse attacks with this page. Now, virtually it's the page being mapped in read-only userland, and the kernel is the one who can access the very same physical page mapped to a different virtual address in kernel land, and it can only actually it can also modify the page then. So getting back to our time example, what's going to happen here is practically the kernel would update in the VVAR section the current time, and then VDSO would then be able to read that time using the VVAR page, which is mapped as read-only from the kernel without actually a need to swap back to the kernel. So this is a huge performance improvement that people very much liked, and VDSO for that reason is also standard nowadays in modern operating systems. After having clarified how the memory is separated between userland and kernel land, let's now have a look at the virtual memory within the process. Basically, there is two major parts in the processor memory, namely stack and heap. And to illustrate you how this works, I'm going to use again the paper. And we're going to now zoom in a single process. That is, we take that part out here and zoom into it, and it becomes the full virtual memory of that one process. Okay, and then we're going to look at how things are organized, and to ease all of the stuff that comes later on in the lecture, I now going to swap the address space. So essentially at the top we're going to have the address OXOOFF and so on, and here we're going to have the lowest possible address 0000. Okay, now let's have a look at how the stack and heap is organized. We're going to introduce the stack at the very top of the memory here, and we're going to introduce the heap kind of at the bottom. Let's say here, heap. Now, what is stack and heap in the first place? In the stack, you store per function addresses, per function data. You store, for example, that local variables are being stored there, everything that can be statically allocated during program launch time. And in the heap, you would store objects which you dynamically allocate during the program runtime, such as, for example, if you allocate huge parts of memory to store an image, then you would very much store that in the heap. And between the stack and the heap here, there's lots of space that can be filled by the stack and heap during runtime. The stack grows from top to bottom, and the heap grows from the bottom to top. So before I mentioned that the stack will contain data that you can allocate during process startup, which is not actually 100% accurate. So for example, when you invoke a new function and another function and yet another function, you can generate a function stack, and all the addresses of these functions will be stored on the stack, which essentially means that over time this stack will grow. So does the heap. The heap starts with a very empty heap, and then you start allocating more and more objects, which will fill the heap here and here and here and here. And at some point, the current heap that you have allocated is filled with objects, and then you just expand the heap towards the middle of the memory space. And back then in the days where we had 32-bit systems, there was actually a good chance that the heap and the stack at some point would collide somewhere here in the middle. But now, since we have a huge 64-bit address space, chances of doing so are actually quite low. Then, in addition to the stack and the heap, we have more so-called sections that are stored in the virtual memory at the very bottom. I'm going to call these just miscellaneous sections. For example, what you can expect here is that your code of the program and some read-only data that are really known in terms of size during load time will be stored at the very bottom of your virtual memory. And this is kind of the separation between stack and heap and how it's organized in the process memory. Getting back to the slides. So again, to repeat, the stack stores things like function parameters, local variables of functions, and return addresses, and some kind of temporary variables. And the heap would store anything that you dynamically allocate yourself, for example, using malloc in C. Now, this already greatly helps to separate between user land and kernel land. And so far, we've assumed that we have a system call interface, for example, for opening a file. But the main question now is, are we actually allowed to open a particular file? And one such mechanism to govern which files or which resources a given subject like a user can open are so-called protection domains. Now, a protection domain is very important because it grants access to several resources like files, devices, and pages to subjects. And a subject in the normal sense will be a user or a user group or a process that belongs to a user. Now, they are actually helpful to have a more fine-grained separation than just user land and kernel land. I mean, imagine you have a file and two users on the system. You want to have the situation where a file belonging to one user cannot be accessed by the other user, right? And this you can actually define by using so-called protection domains. The basic idea here is as follows. You have, as I mentioned, objects, as shown here on the slide. Here, objects, and in the example, I just have a couple of files, file 1, file 2, file 3, file 4, 5, and 6, okay? And then you create so-called protection domains which govern per subject or per collection of subjects what they can actually access. So in the domain 1, you have a couple of users. We can read and write to file 1, read and write to file 2, and read and execute file 3. And the very same file, F3, can also be read and executed for a different group, namely domain 2. And domain 2 can also read file 1, but not write to it, like domain 1, and can, in addition, read and write to file 4. And then you have a completely different domain, domain 3, which is allowed to read file 5 and read and write file 6. So with this, we now have a cool mechanism of actually governing who can access what. Typically, we do this in a so-called protection matrix. So we specify our domains per row, and in the column, we have our resources, in this case 6 files, giving the examples on the previous slide. And here we now have the chance to say, again, in a tabular form, that domain 1 are allowed to access these and that files and not allowed to access these and that files. Now, as you can imagine, these matrices are usually super sparse. You may have hundreds of users on the systems, and you have surely thousands of files on the system, and storing the full table for any potential combination is kind of super inefficient. To make this more efficient, people thought of two different ways how this protection matrix can be stored. One is by column. So for each object, like a file, you remember the domain's privileges. For example, for file 1, you recall that it can be read and write from domain 1, and it can be read from domain 2, and that's it. This is a so-called access control list. So the ACL, we're going to call it the ACL, governs per resource who can access it. The other way to store the protection matrix are capabilities. And the basic idea here is to do this per row and say domain 2, for example, user number 2 can actually read file 1, can read and execute file 3, and read and write file 4. And that's it that you have to remember. And for each domain, you would actually have a different set of capabilities assigned to the domain. Let us now look at an example of access control lists in practice. Unix and Linux use ACLs in order to enforce permissions to files. And all sorts of files in Linux are stored as so-called inodes, and inodes are kind of the metadata structure to store not only the file, but also store meta information, such as, for example, access privileges. And also directories are essentially used and stored as inodes here. For each file, we have a couple of protection bits, and these protection bits now determine who can actually read and write and execute the file. To do so, we have 9 bits, each 3 to read, write, and execute for the owner of the file, for the group that is owning the file, and others. Essentially, others means who is not the owner and not part of the group of the file. So if we, for example, take a look at the example at the bottom, we have the read and write bits set for the user, for the owner. So the owner can read and write the file, and the group of the owner can only read the file, which may comprise of other users in the group. And then you have other users which don't have any bit set, so they don't have the privilege to read nor write to the file. And none of the 3 users has the privilege to actually execute the file. So it's probably some private data that the user is happy to share with others in the same group for reading only, but not to others. On top of these 9 bits, we also have set UID and set GID, which is set user ID and set group ID bits as kind of a special mechanism that if you execute the file, you suddenly execute the file in the domain of the owner's user or the domain of the owner's group. So for example, if you say the set UID bit, if you set this set UID bit, and then any other user would execute the file, the execution of that file would then be within the context of the user that owns the file. Same for set GID, it's just not the owner, but the group of the file. And finally, we have the sticky bit. And the sticky bit is set for directory typically, and that means that only the owner can delete, alter, and rename files in that directory. And all others can only merely list files in that directory. However, these privileges are kind of too coarse-grained in many examples. So right now we can only specify privileges to one user and one group, but typically you want to do more than this. You want to give access to multiple users which are maybe not part of the same group as the file. So you have to think of other mechanisms. And luckily in Linux, there's so-called extended ACLs, which can grant permissions to an arbitrary number of domains. And the facility of doing this is called setFacle, and this is complementary to the standard minimalistic ACLs enforced in Linux. So not only you have to check the 9 bits that we previously mentioned, but also Linux is checking for these extended ACLs and can grant access to the files, although users are not the owner of the file and are not really in the group. So the operating system then iterates over the extended permissions and checks if there's any match with the currently executing user, and if so, would it grant the access. This is the way of actually how to store and what kind of format to store the different policies. So one is to recap capabilities, and the other one is access control list. Now let's have a look at how we actually define these policies. Who can maintain these policies? And there are 2 orthogonal concepts here called discretionary and or mandatory access control. So let's try to separate both. In discretionary access control, you give full control of the privileges of the resource to the user who owns the resource. So the resource owner can pretty much delegate privileges to others, can add other read privileges, for example, to the file and so on. Whereas in mandatory access control, this is different. In mandatory access control, it's only the system administrator who can actually grant privileges and change the security policies. So to cut the story short, in DAC, we allow the owner to change policies, whereas in MAC, this can only be done by the administrator. Let's go through a couple of examples to make these two concepts a bit more applicable. So if you look at Facebook, and Facebook usually have users who want to delegate read privileges to the photos that they post to other particular groups or other users, and this is a clear example of discretionary access control, where the owner has full control over who can actually see the data. Similarly, in Linux, the examples we just discussed, you can have a file and you can pretty much decide who can read that file as an owner. This also is a discretionary access control. If you now look at other Linux mechanisms, you can also find MAC as part of Linux. And one example is SE Linux, where you can specify security policies. We're going to talk about SE Linux in a minute. And then essentially these SE Linux policies have to be maintained by the system administrator, and it's only the administrator who can change them. And another example, which is more concrete, if you, for example, are a bank and you would like to grant certain privileges to your clerks to access customer accounts, but you don't want the clerks to actually delegate these privileges to other clerks, to other employees of the bank, then you can let the administrator enforce these policies. And essentially, then we again have a mandatory access control scheme. Now let's look at two more theoretical concepts about providing integrity and confidentiality in data-owned systems. One such model is the Bell-LaPadula model, which originally stems from the military, where you have objects again and subjects. Objects is like a resource, like a file that we discussed, and subject is again like a user or people that have both a certain security level. And security level for document could be top secret, which is highly classified, or if it's kind of public, and it could be unclassified. And subject could be different people working for the military. So if we stick for that example, it could be the general or the foot soldier, right? So really two different categories with different privileges. The higher your level is, the more trust you have, and the higher is also responsibility. And the one goal of Bell-LaPadula, and which is also guaranteed in theory, is that Bell-LaPadula can prevent information leak from higher to lower security level. So short, if a general creates a super sensitive document, the general does not want the foot soldiers to be able to read that document. This is what we call information leak. To succeed with this, Bell-LaPadula has two very simple security policies. The first one is the simple security property, how it's called, which is the no read up property. Which means a process running at level K can only read subjects with level K prime smaller or equal to K. Okay? So that means that any lower level subject cannot really steal sensitive information. So like the example before, a foot soldier would not be able to read data that is classified as top secret by the general. This is simple to understand and intuitive. The other one is a bit more complex, requires some more thought. The star property, no write down, which implies that a process running at level K can only write to objects that have level K prime prime, which is larger or equal to K. Meaning, in the case of the general can only write to documents which are classified top secret, which is the same security level as the general, or even above, like the president, but the general could not write to documents which are below his security level. Like if the foot soldier creates a document, the general will not be allowed to write to this document. This sounds a bit unintuitive at first, but if you think of it, it perfectly prevents information leak. Even if we had a general which is rogue, which is malicious, and has the intention to leak data to lower levels, for example, leak it to the outside, he cannot, right? Because now he doesn't have the privilege to add any data, copy any data to a lower privilege process. So the intuition here is that you want to prevent that high-level subjects can leak any sort of sensitive information. And in theory, Bella Padula is nice because it guarantees that you don't have information leak. You immediately see that there is, of course, many practical problems with it, because you do also want the generals can write to low level data. But this is, if you follow strictly the model, this is actually theoretically proven that it's working well. Now people, because the limitation I just mentioned, became a bit unhappy with Bella Padula. And then there was Biba, and Biba came up with another model called the Biba model. And whereas the Bella Padula model was designed to keep secret, it doesn't by any means guarantee integrity. Have a look at the example of the general and the foot soldier before. It was forbidden that the general can write data to the foot soldier's level, but it was not forbidden that the foot soldier could actually write data, could overwrite data of the general. Right? So essentially we have no guarantee of integrity. A foot soldier could modify, could even delete the data that the general has written, which is super unsatisfactory. And this is what Biba is actually trying to solve. We, instead of secrecy, want to have integrity. So it's kind of a twisted game now, and the rules, again we have two of them, are kind of the opposite of the rules before. So we again have a simple integrity property, the no write-up policy, which means that if you have a process running at level k, you can only write to subjects with level k prime which are smaller or equal to your current level. Okay, so foot soldier could only write to documents of the class foot soldier and could not write to any top secret documents. The second one is again a bit hard to understand. Again, the integrity start property, no read down. It means that a process running level k can only read objects that have level k prime prime larger or equal k. Meaning, getting back to our example, if the general aims to read a document created by the foot soldier, he cannot. This again is super non-intuitive, but it follows the idea of the Biba model because we want to have integrity. And since the general, if it would read data from the foot soldier's account, he would not have any guarantee that this data is has integrity ensured. So the second property, the integrity start property, ensures this, again in a very theoretic concept. Now, if you have a system that rigorously enforces Biba policies, all information that is stored at the current or higher level has strong integrity guarantees. But again, on the other hand, you don't have any secrecy guarantees. And what is worse now, if you compare Biba and Bella Padula, these two models are in direct contrast. Right? This is a really, really problematic thing, because we either have Biba, which enforces integrity, or we have Bella Padula, which enforces secrecy, but both actually are not achievable at the same time. So these are nice theoretic concepts that can be applied in very security sensitive domains, but in practice they don't really work. So if you even prove them theoretically, there's one more problem that comes up in practice that even aims to evade them. So if I mentioned before the Bella Padula is in principle safe, this is not really true in practice because you have something called side channels or cover channels, and this is what we're going to discuss next. So let's take a look at the confinement problem. This is exactly one problem which makes it apparent that Bella Padula and the Biba model have practical problems. So the confinement problem is the problem of preventing that a confined process cannot leak information that the user of the process considers confidential. And to make this concrete, let me just turn to the whiteboard where I drew already for you one example where you have one system which runs two processes, namely a client and a server, which both run the same hardware and the same operating system kernel. Now, the idea of the confinement problem is that the client wants to use the server, but the server is untrusted by the client. So the client doesn't trust the server, meaning that the client doesn't want to share any sensitive information to the server. Now the server is smart and says, look, client, you can fully trust me because I'm just gonna isolate myself. Okay, so I'm gonna live in this bubble here, and I promise you whatever data you give, I neither store this data nor I'm gonna communicate the data somewhere else. Okay, and then the client is perfectly fine and just send the data to the server, and the server gives the promise that essentially it wouldn't hand on the data. Now, this is again a principle that works in theory. However, there is a problem if you talk about cover channels. So for example, if you have another process running the same system, which we're going to call the collaborator process, then the server and the collaborator could collaborate in order to leak the sensitive data of the client. How would that work? So let me just give you one example how that could work using a so-called side channel. Okay, so if we, for example, have any sort of secret channel between the server and the collaborator, which is not observed by the kernel, which is not observed by the client, then essentially we could leak information from the server to the collaborator and thereby break the security guarantee that the server has promised to make against the client. Essentially, the data would leak. So how could that work? There's various different implementations of cover channels, and I brought you a couple of examples which I think are quite telling. So let me turn back to the slides and move on to the examples. So one example would be that you have a cover channel by file locking. The basic idea is that the confined process and the collaborator, in our case it's the server and the collaboration process, they share the same file system. This is kind of typical if you have two processes that run the same server, exactly our scenario. And for each agreed upon time frame, let's say a frequency of 1 second, the server sends bit 1 by locking a specific file, for example opening it, and sends bit 0 by unlocking this file. And the client actually checks, in this case the client will be the collaborator, checks if the file is locked to determine the cover bit. Okay, so every second the collaborator would check with the server if actually a file that they agreed upon is locked, and if so, it's a 1 bit, or if it's unlocked, it's a 0 bit. Now this is of course a very slow way of communication where you leak 1 bit per second, but essentially there's nothing that prevents you to accelerate the frequency. You could easily turn this into its channel which is able to leak kilobytes of data per second. This is one example where you actually have a shared file system, but things can be even more subtle. Another perfect example of a covered channel is CPU modularization. Unlike with the file locking example, we're not locking files now, but we do lock the CPU kind of in a way. So the server process who wants to leak data, instead of locking files, it heavily utilizes the CPU to leak a 1 bit, and to leak a 0 bit, it would not use the CPU at all. And then the process that would like to read the leaked bits would essentially just have to observe the CPU utilization. Like if you look at the figure below, we see that there is a CPU load which is either 0 or very high, and then based on that we can pretty much infer which bits are currently leaked by the leaking process. And this way is another good example how a server process could here leak data to a collaborating process. Now let's get back to the formal definition of a cover channel. Essentially, a cover channel exists if there is any path of communication that was not designed to be used for communication. And the two examples I mentioned are just two. There are plenty of other ones in normal systems nowadays. And mainly they do exist because resources like the CPUs, like files, but also like RAM and any other that you can think of are shared between different processes on a system, which is even true if you have full virtualization systems, you have virtual machines running parallel on the same hardware, but more on that later. As soon as you have a cover channel mechanism, the security, the provable security guarantees that you get with the Bella Padula systems are kind of undermined and gone in a practical sense. So far we assume that we want to isolate processes on a single operating system. However, what you can also do, which gives you actually even stronger guarantees, is to isolate full systems. So we're going to look at a concept called virtualization. The idea here is that you have one hardware installation, but you would like to run multiple operating systems in parallel, possibly even different ones. So you want to host so-called virtual machines. And each of these virtual machines is a seemingly completely independent system that you can configure regardless of the other virtual machines running in parallel. The virtual machine monitor, the VMM, or also called hypervisor, is the one piece of underlying operating system which governs the different virtual machines. Now, why would you do this? Why would you use virtualizations? There's many reasons for it, and I've just mentioned the two most prominent ones. So first of all, you can efficiently share hardware. It's very typical in the cloud scenario where you have one setup and you would like to use that setup for multiple clients, and each of these clients then get a share with a VM on the same hardware. And as long as not everyone is using the hardware massively, everything actually works well and is also cost efficient. Second one, it's much stricter in a sense to isolate processes from each other than the concepts we've seen before and the concept we're going to see after this chapter. So what are the requirements for virtualizations? Of course, you have to fulfill certain guarantees in order for virtualization to work. One is safety. The hypervisor has to have full control over the virtualized resources, meaning that the underlying VMs must not access the hardware without any way of the hypervisor to intervene here. This is needed actually to strictly isolate VMs from each other. Second one, which is kind of in contrast, however, is that you want to have fidelity. That is, the behavior of programs in a VM should be the same one as if the program would run on real hardware. And now, which is actually in kind of a stark contrast to safety, is efficiency. The program code you would run in a VM should not be significantly slower than if you would run it on a real hardware. So how do we achieve this? We're going to discuss that shortly. There's two ways in principle. There's software and hardware-based virtualization. Software-based virtualization is the idea to translating your program code into some intermediate representation, and then essentially you would emulate devices like disks, like the screen and so on, and then let the program access the emulated devices, which essentially are software devices then. As you can imagine, this is terribly slow. The alternative, and actually since 2005, since we have hardware virtualization, for example, Intel VTX, there is the way to virtualize systems is hardware-based virtualization. The idea here is that you have confinement techniques for VMs which can more or less directly access the hardware whenever possible, but still you want to have the safety guarantees. So how does that work? We have two different ways of doing so, differentiated by two different types of hypervisors. Let's discuss the more efficient one first, type 1 hypervisors. The idea here is that you have a hypervisor which sits between the hardware and the VMs that you launch. So in this example here, you have a Windows VM, you have a Linux VM, and you have the so-called control domains. And all these three systems are virtual machines which run on top of the type 1 hypervisor. And whenever these systems need to access hardware in a sensitive way, they have to go through the type 1 hypervisor, which can thereby guarantee fidelity. So if the hardware like CPU, disk, and so on, these type 1 hypervisor is always in between and can negotiate which VM can use which resource. So essentially the type 1 hypervisor is to a certain extent presenting the same hardware to these VMs and is not necessarily required for the type 1 hypervisor to intervene with each and every hardware interaction. Actually, to be most efficient, you would like the type 1 hypervisor to refrain from any interaction, because this would always mean that you have a context switch from the VM to the hypervisor, which is quite costly. So in this example, we have Windows and Linux running in parallel, and the third one, the control domain, is mainly used to configure the type 1 hypervisor. For example, if you would like to assign more memory, virtual memory, to one of these VMs, you can use the control domain to actually configure the different other VMs on the system. This type of hypervisor is quite common, and examples that you may have heard of are Xen, vSphere, or Hyper-V are used in Windows. Now, in contrast to type 1 hypervisors, we also do have type 2 hypervisors. The idea here is similar, however, the difference is that the hypervisor is not the single part between the VMs and the hardware, but instead you do have a normal host operating system that first sits on the hardware. So let's say you have a typical Linux system, and then on top of this Linux system you add a hypervisor which runs within the operating system and additionally can provide multiple VMs access to kind of virtualized resources. Now this type of hypervisor is more common because it's much easier to configure, and examples you know is VMware Workstations, KVM, or also VirtualBox as used for different lectures here. Now the advantage of this concept is that essentially you can have a typical host with typical host processes running in parallel to a type 2 hypervisor. So in your case, you can easily use your normal system to do much of the homework, but essentially you can then spawn another VM parallel to your normal system and do some VM specific task in the VM. As you can imagine, this concept is a bit slower because you have to go through the operating system always if you would like to access the hardware, even though you are a hypervisor. This was not necessary for the Type 1 hypervisor, which brought its own operating system and had already full control of the hardware. How do we confine VMs? So before we discuss confining processes, kind of isolating processes from each other, how do we do this with VMs? Now, what should be clear is that guests must not be able to control the host, right? The host is kind of like the hypervisor and the hardware, and this should not be controlled by the guests, otherwise the full isolation guarantees we have are gone. So we have to do some rigorous confinement of the hardware, like CPU, memory, and so on. Otherwise, the guests could do nasty stuff. For example, disable interrupts, freely access any input operations of the system, and so on. So essentially, you would like to give the guarantee that guests cannot modify each other and also cannot modify the host. So how do we do this? Essentially, there is multiple ways of doing this which are run in parallel. The first one is that they have to take care of sensitive instructions. If you capture a sensitive instruction, like for example input-output control, then the CPU would trap to the hypervisor. Trap here means that the VM will be interrupted and you get full control of the hypervisor. And the hypervisor has then the full control of what it does. It can actually check why the trap occurred, which operation the VM tried to do, and then based on this action, the hypervisor can decide whether or not this action should be granted or not. So essentially you do have some policies in the hypervisor which are then enforced by every time a trap is being called. And if the trap is called for instruction that is allowed, the hypervisor can actually return back to the VM. If it's not allowed, if it's some non-permissive instruction that hypervisor wants to forbid, it can pretty much kill or destroy the VM. This gives you the full control of enforcing the security policies. Now, one complexity that we have though is that we have now one more layer of virtual addressing. Before, we had a simple translation from virtual memory to physical memory. This is not the case anymore for virtualized systems. So let me just swap to the whiteboard to show you a bit how this now works in practice. So before, in the non-virtualized world, we essentially had a mapping from virtual address to physical address. This is a one-level translation. Now with virtualization, we have something which is one layer more, where we have the guest's virtual address, which translates to the guest physical address, which however is not yet the actual physical address of the host. So that one has to be translated once more to the host physical address. As you can imagine, this involves quite a significant performance overhead, but it's something that is super necessary because otherwise we wouldn't have the full differentiation between the different memory spaces, because it's actually, as you would like every process to have its full virtual memory space, you also would like every VM to be able to use its full virtual memory. So this mapping is required, and the one way how this is implemented typically in practice are nested page tables, or in Intel terminology, the extended page tables. So you do the regular page table lookup from guest virtual address to guest physical address, and then you have the nested page table that translates the second step, namely from the guest physical address to the host physical address. And as you can imagine, all these lookups do require again multi-level page tables and so on, so you would very likely use again the TLB to retain some form of efficiency with all these translations. As you can imagine, full system virtualization is sometimes too heavy and not efficient enough for purposes that actually would only require to properly isolate processes from each other. So in the following, we're going to look at how we can do more fine-grained process isolation techniques. I would actually just try to hide the other processes from each other, or just prevent that one process can intervene with the operation of another process. This is one intention. The other intention is that if a process, for example, after software exploitation, becomes rogue and tries to behave maliciously, how can we prevent the harm by this rogue process? So one basic idea is essentially that you use different user contexts, different domains per process. If you have a single user which has multiple processes, you don't normally have strong isolation between the different processes of that one user. In Linux, you can see the other processes of the same user. You can even stop them. Reading memory is a bit harder, but you can probably do it even with workarounds using ptrace and debugging interface. And in Windows, it's totally easy. There's even an API in Windows that can allow you doing so, maybe read process memory and write process memory, which essentially allows you to open any other process of the same user and read data from the process or even modify data in that process. People have realized this is not ideal, especially if you have multiple processes running in parallel, and started to use separate users and groups for each process, each different process on the system. This actually has become the standard in Android, where every app that you install now has its own user and own group, such that essentially this app cannot easily modify the other applications running in the same system. This is an easy but still a bit coarse-grained mechanism to isolate processes from each other. Let's look a bit more fine-grained process isolation policies that exist, what we can do. For that, let me just enable the whiteboard for a second. Now, what I prepared here essentially is a single system which runs three processes, process 1, process 2, process 3. And we have the operating system at the bottom, which has a couple of components, modules, how you call it, like the file system, like all the processes running, the network, and so on. Now there's different mechanisms what we can do, and before enumerating all of them, let me briefly guide you through what we can do in terms of fine-grained process isolation. The one is that we can actually restrict the process's access to the file system. Essentially, the communication between the file system and the process here can be limited by a feature called change root. The basic idea is that you would confine the process in its own file system part, which is just a subdirectory of the entire file system. There's more what we can do. So imagine that if these processes P1 to P3 want to perform any sensitive operation, they have to go through the operating system anyway, which we learned before is done by the system call handler. So what we can do is we're going to add our syscall interface here on the picture, and for whenever a process would go through this system call interface to actually do any of the operations with the operating system here, we can add more mechanisms that would check whether or not the operation is actually allowed. And there's two alternatives we're going to discuss. One is the so-called seccomp filter, where you can filter which types of system calls should be allowed. And if you want to do it even more fine-grained, you can go for SELinux. And SELinux enables you to actually specify not only what types of system calls, but also in way more detail define policies of what a process is actually allowed. And every time a system call is invoked, either the seccomp filter or the SELinux filter would kick in to check whether or not this is actually allowed. And finally, what you can also do, it's also something we're going to look at, is that you can provide the processes with different so-called namespaces. The idea here is that you have kind of a shield across all these different components of the kernel, and whenever a process would try to intervene with the file system, with the processes and so on, you provide it with a subset of the actual set of files and processes running in the system. This is a technique called namespace. And this is how Linux does it. And if you then look at other operating systems, you're going to find different concepts. For Windows, you have integrity levels, tokens, and job objects, something we're going to look at shortly. But for now, I would like to go through the individual fine-grained techniques in Linux that I've just teasered for you. So let's have a look at change root. The idea of change root is that every process gets its own share of the file system. So you don't see as a process the entire file system, but you're being moved when you start into a small subdirectory of the entire file system, which now becomes your new root directory. In principle, in Linux, every process sees the entire file system, and with change root, you put the process into its small jail, and the process can therefore only see the files that belong to the process. Change root is a very nice principle, but it does have a couple of caveats that you should actually pay attention to if you deploy it in practice. It does not fully give you strict security guarantees because there's a couple of things that might go wrong. For example, if you have pending file descriptors that the process has opened before it was sent to change root, then the process can still access the file descriptors, and they do refer to the entire file system and not to the change root environment of the process. Likewise, if the process opens files in the change root environment, which later on gets transferred to the outside environment, then actually the process does again have a file handle which points to the entire file system. And needless to say, change root is kind of ineffective against root users because they can easily escape from the jail environment. Let's now turn to the two variants which use system call filtering, namely seccomp and SELinux. In seccomp, you restrict the set of system calls a normal process can do. And the main intention behind this is that essentially there's many system calls, over 100, including many unprivileged ones that a process can normally call, but the set of actually required system call for the normal operation of a process is much smaller. So you restrict the process to the system calls it actually needs, and even if the process gets exploited by someone, there's no possibility that the process can invoke any other system calls than the ones allowed on startup. Now, as you can imagine, this greatly reduces the attack surface, especially if processes become compromised by attackers, for example, due to vulnerabilities. Now, there's two ways to define seccomp policies. You can do the default seccomp, which limits a process to invoking exit, sig return, read, and write. So if a process in default seccomp tries to open another file, it cannot, because it can only read from and write to files it had already opened before. As you can imagine, this is nice but quite inflexible. So many times you would like to have policies which are kind of custom. And that you can do with seccomp BPF, where you can actually have configurable policies where you as developer can specify exactly which types of system calls your program needs, and to that set you will be restricted after program startup or after the program has initialized and invokes the seccomp filter. Seccomp is super popular in the Linux world, and many container software like Docker, but also many software repositories that do not container stuff like OpenSSH, KMU, Firefox, and so on, they do use seccomp to simply limit the harm what can be done to the system if the software should be compromised. The other, even more flexible system is SELinux. And SELinux, it adds mandatory access control to Linux. Recall that MAC is a policy that only the administrator can actually change. And this is what SELinux does exactly. When a program joins the system, a new program, then the administrator has to look over the policies that the program brings, add them to the system, allow the process to do certain activities, and it will then also enforce these activities in the system call handler. So essentially in the kernel, you can do rigorous policy enforcement. And the process can only invoke those system calls and do only those actions which are permitted by the SLinux policies. The policies themselves are a bit more flexible than in seccomp, whereas in seccomp you can only restrict the set of system calls being invoked. In SLinux you can also actually control some of the parameters of the system call. To give you a couple of examples, I brought you the SLinux policies of the PostgreSQL database that you can see here at the bottom, which has two rules. The first one would allow PostgreSQL to add new log files. So instead of giving the full privilege to write any file to the system, here you restrict PostgreSQL to only one directory. And second, you restrict here PostgreSQL to binding a given TCP port number, and only that one port can be bound by the PostgreSQL database, and it cannot actually bind any other port. Finally, we'll discuss kernel namespaces. Kernel namespaces in Linux are a way to restrict the view of a process of the overall system the process can see. So for example, you can hide certain processes from the process. So if the process invokes a process list, it would only see a small fraction of the processes that are running on the entire system. And the way this is realized is that you actually have different namespaces in the kernel for different types of modules on the server, in the kernel. Like for example, PID gives a view on the processes running the system that I just mentioned. You have a network namespace for restricting the network configuration and what the process sees in terms of network connectivity. Then we have the mount namespace, which restricts which file systems the process sees. Finally, we have user namespaces, which restrict the view on current system users. So there's a possibility to hide other users on the system from the current one. And namespaces are thus heavily used for container systems because they allow pretty much to make the process they isolate to the illusion essentially to run on a fresh system where the process runs alone, although there's plenty of other processes running next to it. In Windows, the word is a bit different. Windows foresees per process integrity levels, and these integrity levels are essentially 5 levels that determine the type of privileges a certain user and process has. The default is level medium 2, and if you run processes as administrator, you have level 3, and the highest level is reserved for system process at level 4. And if you run an untrusted or low integrity process, then essentially you almost have no privileges whatsoever. And then Windows has 2 rules, the no write up and no read up policy, which sound a bit familiar like a mixture of Bella Padula and Biba rules, where essentially a lower integrity process cannot modify higher integrity objects. At the same time, it can also not read more sensitive objects, like a mixture of both Bella Padula and Biba models. One essential component in here is the access token, and the access token is actually the security identifier of all the processes running in Windows. Every process has its own access token, and when a process spawns a new process, it will even inherit this access token to the new child process. And this token essentially identifies whatever the privileges are of the process, the account and the group the process belongs to, and so on. And these privileges can be quite fine-grained in Windows, so you can actually define privileges to access files and directories like Linux, or similar if you have named or anonymous pipes, like another sort of file in Windows, to processes, threads, registry keys, and so on. Finally, again, like the last lectures, I can also only recommend that you should read the following chapters from the Tannenbaum and Boss book, Modern Operating Systems, which you can find in Chapter 7, Chapter 9.3, and Chapter 9.4, essentially about virtualization, then access control, and securing operating systems. And optionally, if you like, you can have a look at the Chrome sandbox, which is a quite nice way how you can actually put the Windows-based security mechanisms into practice. So if you're curious about the internals here, it's a very nice read.